Of course, I don't know whether before now you've come across this. Has anybody come across that? Z-score, right? Okay. We actually also want to look at moment about Z. Okay. Now, if I actually want to do this, this raised to power R, okay, this is the same thing as this guy here, okay. And what are we going to call it? We're going to call it R standardized, okay, R standardized moment. Okay, we're going to call that R standardized moment. Okay, you know, when R equal to 1, obviously this is going to be 0. We don't need that. Okay, R, the first R standardized moment is not of statistical interest. Okay, for R equal to 1. Okay, this is going to be 0 because for R equal to 1, don't forget expectation of X minus expectation of mu, which is mu. So expectation of X is mu, mu minus mu. When the numerator is 0, of course the whole thing is going to be 0. Now let's see when R equal to when R equal to 1, we said it's going to be 0. Okay, when R equal to 2, what happened? Can somebody tell me? When R equal to 2, what would be the result? Can somebody tell me? When I plug in 2 here, what is going to happen? What is the answer? When R equal to 2, do you want to work it out? Yeah. 1. Send me a message for extra credit. Okay? Yeah, send me a message for extra credit. Okay, like I said, you can be accumulating your extra credit point, and imagine you score 90% in the final and you have 10 points of extra credit. You can advise me that, okay, I want to spend my 10 extra credit point on the final. You know what I'm going to do? I'm just going to do 90 plus 10, and you're going to have 100. Okay, I don't joke with my extra credit point if you answer my question correctly in class. Okay, now when R equal to 2, the reason for that, now when R equal to 2, so which means I want to do this guy now, which is going to be this minus this sigma all squared, and this is going to be this all squared divided by sigma squared. And you know what? When you take a look at this guy, this is a variance of S. Okay, the variance of S is the same thing as sigma squared. That is the reason. Does that make sense? For us to live successfully in a stochastic world or in a mathematical world, then we got to reason mathematically. Does that make sense? Okay, now, this is not also of interest to us right now. You know what is of interest? What is of interest is the third standardized movement. Okay, like I said, the first standardized moment is going to give us 0. The second standardized moment is giving us 1. And you know what? The third standardized moment is what I want to talk about right now. So expectation of Z raised to power 3. Okay, so which is this or that raised to power 3. Oh my God! When you take a look at this guy now, this is divided by that. This is what we call skewness in statistics. Skewness in statistics. Now let me tell you the significance of skewness. If I have a probability distribution, you know, if you really want to, you want to deal with your data, right? You need to be able to understand your data. Okay, understanding your data, you'll be able to know the appropriate statistical model to use. Relationship between data and researcher or relationship between data and statistician is the same as the relationship between a patient and a physician. Does that make sense? A patient needs to understand the nature of the illness, before intervention. Okay. Now, let me tell you this: is when we are working with data, okay, we may need something beyond mean and variance. We actually want to know whether the shape of the distribution is it going to be, is the data skewed? Skewness is talking about, okay, now take a look at this. I don't know whether some of you have seen the shape of a normal distribution. This is the shape of a normal distribution. It is expected that it should be symmetric in nature, where the tail here should be equal to the tail here. Okay, situation where it is a situation like this. That's a skewness. Okay, we got a positive skewness, we got a negative skewness. Okay, now, and that is the reason why this is very, very essential when I have a data set. Okay, when the data set is skewed, then I need a statistical model that we actually incorporate skewness. This is what happens in a stochastic world. We want to depict reality using a model. There must be an agreement between a model and reality. If you're using a wrong model, okay, a wrong model is the one that disagree with reality. You are never going to get something meaningful. And that is the reason why if there's a skewness in my data, then I need to use a model that incorporates skewness. Does that make sense? And that is the reason why we're doing all of this. Like, for instance, if you talk about income data, okay, income data, does not follow normal distribution. Income data exhibit positive skewness because you're actually going to have majority of low income earners and few, high income earners. That is skewed to the right. Okay. Now, if I want to, so which means skewness actually is a measure of asymmetry. Asymmetry. Okay, a measure of the asymmetry is a measure of the departure of data from normality. Okay, now if I want to find that skewness right now, mathematically speaking, from a distribution, this is what I need to find. Okay, this is actually what I need to find. Of course, you know how to get this, and what is this? This is just after the cube of the standard deviation. Does that mean saying the cube? You already know this. The sigma square is this, right? The sigma square is this guy, right? You know how to derive that. Okay, then the sigma is actually going to be square root of that, right? It's going to be square root of that, right? Okay, sorry. It's going to be square root of that. So the moment you get this sigma, you're just going to raise it to power 3 here in the denominator. And from here, oh my God, the numerator here is the third moment about the mean that I've discussed today. The third moment about the mean. Okay, now that is for the skewness. This is for the skewness. Okay, that is for the skewness. The next one is actually when I record a 4. Okay, then I want to do this guy. What is the essence of doing this? Raise it to power 4. Okay, this is the fourth, we call this fourth standardized movement. The first standardized movement will enable us to get kurtosis. Okay, now what is the essence of kurtosis? Kurtosis measure tail heaviness. Okay, so it measures tail heaviness and peak sharpness. Okay, let me tell you this. Some of you, I'm actually going to talk about this application of kurtosis in finance. Okay, do you know that I kurtosis? Okay, what is going to be the threshold? I think I need to first give you the threshold to be able to know. When you compute this guy and skewness equal to 0, then it means the data set is normally distributed. When skewness equal to 0. Okay, but when the skewness is greater than 0, that's a positive skewness. When skewness is less than 0, that's a negative skewness. Now, what is the threshold for kurtosis? Okay, I'm actually the threshold. The kurtosis of a normal distribution is 3. That is the standard. The kurtosis of a normal distribution is 3. When you get a kurtosis 3, okay, from a data set, that data set is telling you, oh, I'm normally distributed. Which we call mesokurtic. Okay, when the kurtosis